A 40% increase in revenue. Looks great on your dashboard until your boss asks,
what caused it?
You changed the homepage, the pricing, the checkout, and the sales went up, but you have no idea why. Are your customers actually price sensitive, or is just a change in the wind? So you decided to simplify. You changed one thing, the checkout button color. Conversions go from 10 to 12%. It looks like a win, but maybe those users were just more likely to buy anyway. Maybe it was a payday. The increase might be real, or it might be noise. And this is why hypothesis testing exists. Sales go up and down naturally. Users behave differently every day, and sometimes things improve even if you do nothing. If you look at a 40% increase and say, that worked, you're not doing data science. You are just making a story with numbers. The real question is how you separate an actual impact from random noise. Today, we're gonna take a look at hypothesis testing, what it is, how it works, and how can you use it to make it actual decisions instead of relying on guesswork. The basics of hypothesis testing are as follows. Hypothesis testing is started with a default assumption. This change had no effect, and that's your null hypothesis. And then you ask one question, if there was truly no effect, how likely is that I will still see these results? And the probability is your p-value. Say your p-value is 0.5. That means if your change did nothing, you still see the result this big half the time. A coin flip, but there's no evidence of anything. Say if it was 0.2, and now you will see it 1 in 5 times by chance alone. Still not convincing, but if it falls to 0.02, things start to shift. Now you are saying if nothing actually happens, a result this extreme will only show up 2% of the time, and that's unusual. And this is the key turning point. At some level of unusual, the explanation of random noises stopped being convincing, and by convention, that cutoff is 5%. So when your p-value drops below 0.05, you reject the null hypothesis, and it's not because you have proven that your change works, it's because that nothing happened explanation no longer fits the data very well. And that distinction matters more than it sounds. But notice what you're not saying. You're not saying this is definitely works. You're saying that it's unlikely to happen by chance. And that's subtle but important distinction, and is actually a known limitation of this entire approach. Frequentist statistics, which is what we've been describing, can only make probability statements about data. It cannot tell you the probability that your hypothesis is actually true. It tells you how surprised you should be by your results, not whether your results means what you think it means. And there's actually a known limitation of everything we're covering today. There's a whole nother approach called Bayesian statistics that flips that question around entirely, but it's a whole video on its own. For now, just hold on to these. A low p-value is not proof. Is evidence. Keep that difference in your head and you avoid the most common mistake that people make reading those results. Before you run any test, there are a few decisions that you need to make. The first one sounds obvious, but is where most people go wrong. You need one defined metric before you see the data and not after. Is that the conversion rate, the average order value, the time on the page? Pick one. If you wait until the results come in and then choose a metric that moves, you're not doing hypothesis testing. You're just finding a number that supports whatever you already wanted to believe. And this is called p-hacking, and it's more common than anyone admits. One chain, one metric, decided in advance. Once you have the metric, you need to make one more decision before running anything. Are you looking for a change in one direction or any direction? If you change a button color and you only care if the conversion goes up, there's a one-tail test. You're focused in one direction of the distribution, but if the change goes either way, up or down, there's a two-tailed test. Does the new neon green button color encourage sale, or does it actually put people off? You're watching both ends. And the rule of thumb is simple. Unless you have a strong reason to only care about one direction, use the two-tailed test. It's more conservative, harder to hit significant, and that's the point. The one-tailed tests are easier to pass, which is exactly why it gets abused. Now you know what you're testing, which direction you care about. The next question is what tests you actually run. Most people stop here and Google which statistic test should I use and just copy whatever comes first. So let's try to understand the situation first. So instead of giving you a formula lookup table, let's talk about what is actually happening in the real world when each of those tests shows up. Imagine you have thousands of users going through your checkout. Your data is stable, the variance is already well understood. In order to find out whether the spike you see is real, the question becomes how far you observed result is from what you expected, relative to how much variation you normally see. And that's what the z-test measures. It standardizes the difference between your observed mean and your expected mean, and scaled by the variability in the data. If your conversion rate jumps, it tells you whether that jump is actually unusual or it's just a part of normal fluctuation. And this is what large-scale stable data looks like. But now, make this more realistic. You don't have 1,000 users, you have 25. You don't have years of historical data telling you how much the conversion rate normally bounce around. So you calculate the variance yourself from your sample. The problem is that the estimate is uncertain too. With 25 data points, if you happen to catch a few unusually good or bad days, your variance estimate is skewed and you don't have enough data points to smooth that out. And the estimate itself is unreliable. And that's the situation the t-test is designed for. At the highest level, it works exactly like a z-test. You're still measuring how far a result is from what you expected, scaled by the variability. And the key difference is where the variability comes from. With the z-test, you plug a known population variance, something stable backed by a lot of prior data. And with the t-test, you don't have that luxury. You estimate it from your sample. And because that input is unreliable, the test adjusts. So you're not just uncertain about the results, you're unsure how unsure you are. So the t-distribution spreads wider to reflect that. The smaller your sample, the wider it spreads, and the harder it gets to claim significance. And that's not a flaw. That's the test being honest about what you actually know. So your choice comes down to, do you know the true variance in the data set? Or are you estimating it? But that assumes that your outcome is a number in the first place. What happens when it isn't? Say you run an A/B test on your checkout page. 500 users see the old design and 500 users see the new one. On the old design, 80 convert. On the new one, 110 convert. So you have a table, 2 groups, 2 outcomes, and raw counts. And that's not an average, that's a pattern. And the question is whether that pattern is different from what you expected if the design made no difference at all. And that's what chi-square test measures. If the gap between your observed count and your expected count is larger enough that it is unlikely to be a noise, something real is happening. Now it's clear again, you are no longer comparing 2 groups, you're comparing 3 or more. Maybe you tested different buttons colors across multiple regions or different versions of a page. Now that the question is whether any of those groups behave differently from the others. And that's what ANOVA test is. It compares the variation between groups to the variation within groups. If the difference between groups are large relative to the noise within them, then at least one of the groups is meaningfully different. But ANOVA doesn't tell you which ones. It tells you that something is different, not what is different. For that, you will need to go a level deeper with something like 2 key honestly significant difference, the HSD test. Drop a comment if you want to see us cover that topic, but for now, ANOVA is a filter, and it tells you whether it's worth digging further. 4 tests, 4 situations. And if your boss walked in right now and asked you which ones apply to your checkout data, could you answer it? Instead of memorizing formulas, think in terms of situations. If you have a large data set with a null variance, use a z-test. If you have a small sample of unknown variance, use the t-test. If you are dealing with category outcome, use the chi-square test. If you're comparing more than 2 groups, use ANOVA. And before any of that, decide whether you care about one direction or both. Here's what actually comes up in a data science interview. They won't ask you to recite formulas. They will give you a scenario and ask which test would you use and why. You ran an experiment on 20 users. Conversion went up. Was it significant? Small sample unknown variance, that's a t-test. A two-tailed unless you have a strong prior reason to only care about increase. The formula is almost never the answer that they want. The reasoning is. Anyone can report a result. Anyone can say the revenue went up. The real skill is proving whether the results means anything. Did it actually work, or did it just get lucky? And that's the question that hypothesis testing is built to answer.